So it's 7:30. Just a couple of things before we start. So this is the last set of slides for chapter 3. As I mentioned, you can do all of homework 1. So homework 1 is due a week from now. So it's due before class on Friday. And just a reminder, the homework is a fixed template. So I'm expecting the answers where I provide the area for an answer. And I did provide the Word doc just because we can work on it. It's still the same format. We submit it to Gradescope as a view. The other thing is exam 1 is going to be covering chapters 1, 2, and 3. And next week, Monday and Wednesday, we'll do a review. Friday will be new content from chapter 4, but it will not be on the exam. Exam will be the Monday after. And for the exam, I have also posted a exam study guide. I posted the exam study guide solutions. I would suggest that you work on the study guide before looking at the solutions. And then you can like double check your work with the solutions. And there's also a submission on Gradescope for the study guide. It is optional. So the study guide is extra credit. It will go towards the participation category of our grades. And it's 6 lecture days of extra credit if you turn in the study. And it's based on completeness. I'm not going to grade it for correctness. So if you have it complete, you've attempted every single problem, you'll get 6 points. If you're missing 1, 2 problems, you'll get 0 points. So you need to complete the whole thing. Yeah.
Have you had an experience with people, right? Like I'm doing like my homework where I'm writing it and it's scanning it in.
Yeah,
Have you had
that's-
experience where Gradescope
Yeah.
still gets the format up correct?
So just as long as you print out the PDF
Mhm.
as it is, and then you scan it with like Office Lens or some other software that gets it a neat square rather than just like a picture of it,
Okay,
it's perfectly fine.
alrighty, thank you.
Any other question? All right. So we've finished all of our instructions on MIPS and covered the different formats. And today I'm going to talk a little bit about compilers as well as have some other examples of Excel. So here is our compiler graphs. So this graph, it has the relative performance. So with no compiler optimization, performance is just 1. So this is what everything is relative to. And these are the 3 different levels of optimization. So there's 1 level of optimization, O2, and then O3 is the highest level of optimization. And this is for GCC. So if you have ever used GCC and the -O, this is what you're saying. I will either do 0 optimization and just translate the code as it is, do some level of optimization that is going to take a little bit longer, and then I can do more, but it'll again take longer to compile because I'm trying to optimize more. And again. And for the application that is tested here, you can see that the time required to do the next levels of optimization may not be worth it. Just O1 gives you very similar performance between O2 and O3. And we can also see our different aspects of this performance across all of these different graphs, right? We have instruction counts, clock cycles, and CPI. And as you can see with the clock cycles, with optimization, it's able to reduce the clock cycles almost uniformly across the 3. instruction counts. The O1 offers the smallest instruction counts, but because it has this higher CPI is why it's a little bit worse. And this was all compiled GCC on a Pentium 4. The one thing that we want to also look at with our compilers is here we have different algorithms. They're all sorting algorithms, right? And again, we have the relative performance to no optimization. And the other thing that we have here is across the same algorithms, we have C code as well as now Java. And we can see bubble sort, quick sort, and quick sort versus bubble sort. So what we want to highlight between the quick sort versus bubble sort is that the impact of the algorithm of quick sort versus bubble sort is giving 3 times the performance. So although the compiler has this capability to optimize the code with O1, O2, and O3, the 3 different levels of optimization, if you give it garbage in, a bad algorithm, it's going to give you garbage out, right? You give it a good algorithm to go with your application, then it's going to be giving you better performance. So it's still important to use your programming skills, big O notation, figure out what algorithm is best for your application to help the compiler give you the best code. And the other impact is if performance is a key metric for you, choosing your programming language can also be important because Java, it will do your memory management for you. So that's quite a lot of overhead. If you don't really care about your performance, Java might be what you use. But if you care about performance, you're going to want to use a lower level programming language like C. And if you really, really care about performance, you're skipping the compiler altogether and you're coding in assembly. All right. So the question is, why do we think that the programming language matters? They're all targeting the same ISA in the end, right? All of these were running on the Intel CPU, the Pentium 4. Why is it that these programming languages give different performance with the same algorithm? And your code for today is 204. I'm still thinking about this one. Right. So we're close to the threshold, but not quite there. So do talk to the people around you, discuss each one of these things, why you think is one of the reasons why you think maybe it's not. See if we can converge more towards the right answer.
Target different ISA, but don't know if it's level or is it? Is it? It's just me. Okay. It's where you see, and then there's job and then there's. Or you think SAC is the whole, like, nobody can reach it. Do you think it's?
It's really ISA, it might be just brain fart.
I was thinking it's just that you go search that architecture.
Right, is it the compiler or that, or does it go even lower than that?
Yeah, here's discussion diverting, so do change your answer if you were convinced to change your answer. Right, so we did have some movement. Let's go over this together and let's do it one at a time. So are they targeting different ISA? Yes, no? No. All of these were running on the same CPU. Right, sure. Same Pentium 4, same x86 ISA. So the ISA is not the reason. Okay. But what about C is a lower level programming language?
Yes.
This is true, but why does this help us?
Memory management.
Yeah, so like we talked about, you can do your own memory management. You can't, it's possible to make it inefficient. But usually with this level of granularity, you're able to get better performance. But you do have to do proper memory management in order to achieve it. And then C, Java's compiler is not as optimized. Like this? Do we not like this? Yes, no?
We like it.
Okay. So how is Java's compiler not optimized?
It's supposed to be able to run on a wide variety of things, so.
I mean, C can run on a wide variety of things. C compiler can compile for ARM, compile for x86, compile for MIPS.
Or overhead?
Yeah, it's mostly more overhead. So it has that garbage collector.
Okay.
So it's again, you can point towards memory management as one of the things. But mostly it's just the more overhead in terms of the programming language. So we like D so far and we don't like E because we don't like A, right? So this one is D. Okay, B and C.
Let me straight again.
Alright. So like we've been mentioning throughout the
And the chips.
first few chapters, instruction count and CPI are not good performance indicators in isolation, as well as cycle time, right? You have to look at all three of them in conjunction together. And compiler optimizations are sensitive to the algorithm. So like we talked about, if you give it garbage in, the compiler is going to give you garbage out, right? And then depending on the programming language you're using, you can have poor performance because of overhead or not being able to do your own memory management. Right, so now we can talk a little bit about some different alternative architectures. So ARM is the most popular embedded core architecture. So you can find ARM in all kinds of things. Most likely the chips in your car is using ARM. I mean, even pretty much all phones are using ARM. I don't know of a single phone that is not using ARM. What else? Like the computers and airplanes, they use ARM. Things like that. And they are similar to MIPS in that it is a RISC architecture. And ARM actually stands for Advanced RISC Machine. So, and they were kind of developed around the same time, ARM and MIPS. The big difference between ARM and MIPS is that ARM has more data addressing modes and less registers. But something that we will talk about much later in the course, and it'll be something that you guys will talk about with your research project presentation. The physical register file, it doesn't really matter what sense it is. Like, well, this virtual register file, it doesn't matter what, you can have more physical registers. You just rename them and you can have 64, 128 registers. The compiler doesn't need to know about them. You can rename them on the fly in the scene. All right. So comparing branching between MIPS and ARM. So there are conditional execution instructions in ARM. So rather than having to do a branch to skip an instruction or to not skip an instruction, you can have the condition baked into the instruction in ARM. So the top 4 bits of an instruction are this condition value in ARM. And it lets you avoid branching for single instructions. So these are the condition codes for the result of arithmetic or logical instruction. So N is for a negative ALU result, Z is for 0, C is for overflow after a shift, V is for overflow after signed arithmetic. And we have these compare instructions to set the condition codes without keeping the result. Right. So to execute an instruction conditionally, we just postfix it with the appropriate condition. So if you have an add, so R0, R1, R2, so very similar to MIPS, this would be your destination. This is the first register, this is the second register. And you would do R1 plus R2 into R0. If you wanted to conditionally execute this, you just have add EQ. So now, if the 0 flag was set from some previous instruction, then this instruction would be executed. Otherwise, it would be skipped.
Is the semicolon in front or if it would?
Not really important in this case. It's just the separator. This is the instruction, this is what it's doing. So here is what it would look like without this, right? So we have the comparison, then we have the check from the comparison. So this would be like your set less than or whatever. Then your branch, then the instruction. Now we just do comparison to set the register. So is R3 equal to 0? Then add not equal. Okay. So it gives you better code density by doing this. So by default, data processing operations do not affect the condition flags. Apart from the comparison instructions, where that is the only thing that they're doing, right? So if it wasn't default for those, they would do nothing, right? But you can also update the flags with normal instructions. So if we add this postfix s, that will now set the condition flags. So we don't even need the compare instruction in many cases. So add s, R0, R1, R2. We'll still do R1, R2, put it into R0. Now, if the arithmetic result is overflow, that flag would be set. So here is an example of this while loop and the if statements in the while loop. So the beginning of the loop, we're going to compare these two registers. That's going to set the conditions for if they're not equal, greater than, or less than. It will set all of these conditions. Then sub greater than, because if we were greater than, we should subtract. So if it's not set by this compare instruction, it just gets skipped. Right? It doesn't really get skipped, but it just doesn't save to the register file, right? And then sub on less than, we're doing this subtraction. If it was less than. And again, if the less than flag wasn't set, because the greater than flag was set, then the result would not be saved into the register holding the variable j. And then we can branch not equal to go back to the loop if our while condition is still true. So it's a lot more compact code than what we've seen from MIPS. Okay. All right, so here is the instruction encoding for ARM. So we have that condition code here, and then it's the opcode. And then we have the registers, and here it's like the funct code from MIPS, and you have your second register. And then for data transfer, so this is your load word, store word. We again have that condition code, the opcode, two registers, and we have less immediate for a constant because of this condition code. But like we mentioned for MIPS, most branching, most like even memory where you need this constant, it's going to be local, and for the memory you have that base address, right? So this isn't really a problem to have less of your immediates. Every now and then maybe you'll have to calculate the base address a little bit further away. And then for branching, we have our condition code again. The opcode is a little bit of a smaller size in this case. So we have two different opcode sizes for ARM, and we have this very long constant. And then for a jump, it's the same format as the branch. So this is just a different ISA, same RISC architecture idea, but I just wanted to show you that there are other things that exist, although we focus on those, right? So the opposite of RISC is CISC, so complex instruction set computer. And Intel's x86 is an example of this, and x86 is in almost all consumer desktop computers, and it is used in many, many different servers as well, although ARM is also kind of cracking into that market share as well. That's like the computer that I'm using for presenting here. It's using x86. And I see Windows laptops, those are using x86, most likely. There are some Windows laptops running ARM, but there are not many of them. But Mac is using ARM. New Macs, I should say. So the new M1, M2 chips, those are ARM based, but all Macs prior to that were also using x86. So CISC provides more powerful instructions with the goal to reduce the total number of instructions executed. But the problem with implementing more powerful instructions in hardware is that it can lead to slower cycle times and or a higher CPI. Okay. So here is the evolution of x86. Started with the 8080 in 1974, which was a 8-bit microprocessor, and it had an accumulator architecture. And then it moved to 16 bits and became its more complex instruction sets. Here it was more RISC-like, but now it evolved to be more complex. In 1980, it added floating points, 24-bit addressing later on, 32 bits extension from 16 bits. And then as we keep going on, when we reached the late 80s, early 90s, we were adding pipeline on-chip caches. And in the early 90s, we introduced Superscalar and a 64-bit data path, extending beyond the 32 bits. 64 bits is still used today. And then in 1995, it had the Pentium 2, which had a multi-core architecture. And in 1999, they added SMID or SIM instructions. This is same instruction, multiple data. So this is how they're doing complex vector or matrix instructions in one instruction. So it's going to have multiple different associated registers. You just specify the first one, and then it just says the next 4 as well. And then for the other operand, first one, next 4, something like that. And then we have the Pentium 4 in 2001. And further, we are seeing more instruction types, more features added to the x86, I'd say. So it keeps evolving. All right. So one thing that we have to keep in mind is the whole reason that we have ISAs in general is for compatibility, right? So as we keep adding more and more of these features to an ISA like x86, we want to still make sure that all of the legacy instructions are supported and also implemented on processors so that we can still run older programs. Okay. So if we didn't do that, then those older programs that maybe are neglected, not developed anymore, they're not going to be compiled again. They just would not work on new CPUs today. So you have to keep that in mind when you're adding these features. You need to still be backwards compatible. Yeah, and x86 is very popular on desktop or family computers. We don't really have family computers nowadays. Usually, most households have multiple computers now. Those computers have become much cheaper, but back then computers were not very cheap. Like the family computer in the 90s, equivalent to dollars today, was probably around $5,000 today's dollars. So you're not going to get one of those for each one of your kids. All right. So the other thing though is if you don't evolve your ISA to extend its capabilities, then your competitors for sure are going to, like ARM, right? So ARM and x86 are competitors. So here are some fallacies with the x86 or CISC architectures in general. So we have powerful instructions. And we would think that because we have more powerful instructions, we would always lead to higher performance. But as we mentioned, this is not always the case. We do have fewer instructions required, but these complex instructions are very hard to implement efficiently and quickly in hardware. And because you need to implement all of the ISA, and you're implementing those complex instructions, many of your other less complex instructions are going to be slowed down because of needing to have your cycle time accommodate the longest instruction. And this can be very bad depending on your application. So if your application is not using any of the powerful instructions, then it's going to have worse performance on a CISC architecture compared to a RISC architecture. And the other thing is compilers are very good at making fast code from simple instructions, very bad at making fast code from complex instructions. So the other thing is that you might use assembly code for higher performance. But for many modern compilers, they're going to be better at dealing with modern CISC architecture processors. But for some other embedded applications, depending on the ISA, people still do code in assembly. All right. So we talked about backwards compatibility, and we don't want to change existing instructions. We just add instructions if we want more instructions. So x86, from the graph, you can see the instruction count has increased over the years. And on average, it was more than one instruction per month over 35 years. Of course, it's not like actually one instruction added every month. It's just when these updates were added, but it just shows how many more instructions were implemented. All right, so here's our summary for MIPS. We have these 32 registers. They're for quick data referencing. So you load from memory, put what you need to work on in the registers, work on them. When you're done, you put it back in memory and then load the next set. Okay. And you have 2 to the 30 memory words or 2 to the 32 memory bytes, right? That are accessible from the 32-bit register addresses that MIPS is providing with MIPS 32. And we have these 3 different instruction formats. R types are for what type of instruction?
Register.
Register. I types are for?
Immediates.
So register
And
plus some immediates into another register, but it's also used for other things that are not going to be stored in register, like branching, load word, store word. And then J types are only for the different kinds of gems. Yes. So this is just control. And these are your different instructions. Again, this is on not this exact table, but all the information on this table is on your MIPS sheet. So again, instruction complexity is only one variable. We need to consider instruction count, CPI, and cycle time when we're talking about performance. And we need to follow these simple principles to get better performance. We like the simplicity and regularity. So that's where it goes back to very simple, like RISC architecture, very simple instructions are very easy to implement. And they would also be more regularly used than the complex instructions in CISC architectures. And that goes with smaller is faster, right? If your instruction is only doing add, it's going to be much simpler and faster to implement in hardware than if your instruction is, say, adding a vector with a vector or multiplying a vector with a vector, like that. And good design demands that we make these compromises. So, like how we have this compromise of, we have the 16-bit immediate. And oftentimes you are making compromises between instruction count, CPI, and cycle time. And again, we want to make the common case fast, right? This is from which law? Amdahl's law. So Amdahl's law says make the common case fast because your performance is going to be limited by the proportion that you're impacting. So if you're making an instruction that you're only using 10% of your total execution time for, you can only achieve a 1.1 times speed up, even if that means that you totally optimize it and take 0 time, right? So you should target the part of your program or the part of your ISA that is most often used. The other thing is instruction set architecture. It's a very important abstraction because of why? Why do we care about instruction set architecture?
We don't code in 1 and zeros.
So yes, so that's for the abstraction, so that you don't have to use your punch cards anymore. You have the assembly language, and then you have the high-level compiler. But why do we care about specifically instruction set architecture? Why is that layer of the abstraction super important?
So hardware and software.
Yes, it's the divide between hardware and software.
It really determines like the complexity of what things get broken down to. So whether you have a lot of overhead in what you need each instruction to do or not.
So it defines a lot about our performance. What's another thing though? That's a really important one though. It does define your performance. It's the principles risk versus six. Like you need to decide that before you even start making the instruction set architecture. But there's one more very important thing about ISA.
They're different for all computers, so, or like every computer, so,
Not every computer. I mean, lots of like Intel and AMD, they both use x86 ISA, but it's not different for every computer. But what's above the ISA? And the abstraction layers. The compiler, and so what does the compiler take in order to, so the compiler is kind of the in-between, right? Compiler takes what's in and spits out the assembly code.
level language.
So yeah, it takes in your code, right?
Yeah.
So with the abstraction layer, I can then write code once, compile it for x86, compile it for ARM, compile it for MIPS, right? I don't have to rewrite my code. So it increases portability, and again, like you said, the other very important thing is performance. Right, so like I mentioned, exam 1 study guide was released. is 6 lecture participation days if you submit it on Gradescope before the exam. There's no reading for next lecture because, again, 1 second. Monday and Wednesday are going to be review days to prepare you for the exam on the next Monday. And Friday, we will start new content, but it won't be on the exam.
Is the study guide the same format like the homework, like you have like the volume?
Yeah.
Okay.
Yeah.
Any other questions?
You want it? We don't have to turn it into Canvas, just Grayscope.
Yeah, everything is turned into Gradescope. And this is just with the files. I also put the due dates on Canvas, but the due dates are also.
No, you can put it on.